Okay, so what we have done, so first of all, a reminder, you've got an exam on Wednesday. It's the same format as the last one. I haven't quite finished writing it yet, but it should be about the same length as the last one as well. And as I mentioned, it should cover more or less everything that we did in chapter 3, with possibly some of the very basics of the stuff that I talked about for higher order differential equations on Friday. I only really got started, so you shouldn't spend too much time on the higher order linear differential equations. On the other hand, we're going to finish higher order linear differential equations today, and you'll see that pretty much all the answers that you know from second order linear differential equations transfer over to higher order linear differential equations, so nothing is very surprising. And I gave a list of the topics that I wanted you to be comfortable with on Friday, so if you missed that, you can take a look at the video Friday. And my plan, and just to let you know, so today we're going to do all that we are going to do in chapter 4, which is higher order linear differential equations. And then starting today, and then for the rest of our time together, which is through next Monday, we'll be working in chapter 7, which is systems of first order linear differential, or systems of first order differential equations, not necessarily linear. So
sorry to interrupt. Just quick.
Yeah, sure.
Like on Connect Carolina, it says the last day of class is June 18th, but is it true that the final's on the 17th? I think that's the Wednesday.
That's correct. So there's the last day of class is Monday, the 15th. The 16th is a reading day, and then exams are either on the 17th or the 18th, depending on your class schedule. And according to when our class takes place, it should be on the 17th.
Okay, thank you very much.
Yeah, please, I'd urge you to look up the final schedule on your own and make sure that all that I'm saying is correct. Any other questions about finals or things like that? Okay. Where was I? I have no idea. Oh yes, I was saying for the rest of the class, we're essentially going to cover sections 4.1 and 4.2, and then move on to chapter 7 and do as much as we can of chapter 7. So that's the structure for the rest of the class, sections 4.1, 4.2, and then 7 for the rest of class. Chapter. So if you feel like getting ahead and reading forward, do your reading in chapter 7. Okay, let's continue then in chapter 4, discussing higher order linear differential equations. So what we discussed last time is we discussed what should we expect from IVPs. Or what do we expect in terms of data to give a unique solution? And essentially the data is you need up to n-1 order data. That is, you need a y of t0, which is like 0th order data. You need y prime of t0, which is what I could call first order data, all the way up to the n-1st derivative of your function y evaluated at t0. So this is n pieces of data, n numbers. These should be enough to specify a unique solution to a order n differential equation. We know about existence and uniqueness. And essentially, it's the same result as we had for second order. when you write out a differential equation like y to the nth derivative plus p1 of t y to the n minus 1 plus p2 of t y to the n minus 2 plus all the way down to pn of t y being equal to g of t, then we have existence and uniqueness on an interval containing the initial data on which all of the functions p1 through pn and g of t are continuous. And you get a solution that extends exactly that far. We expect n-dimensional families of solutions. Or another way to put this is we expect n, like a system of fundamental solutions, should consist of n functions. And once again, we have a condition for checking when a collection of n functions actually constitutes a fundamental system for the differential equation in question. And what is that?
The Wronskian.
Exactly. To check whether y1 through yn form a fundamental system, check that the Wronskian w of y1 all the way up through yn of t, which is equal to the determinant of the lines of derivatives y1 prime all the way down to y1 n minus 1 derivatives all the way up to yn prime all the way up to y n minus 1 n of t is not the zero function. Oh, sorry. Okay. This is all review from yesterday, so is there any piece or part of this that y'all have questions on? Also, I just want to comment, make a comment here. The reason why it's enough to check the Wronskian depends on the existence and uniqueness theorem. The point is, if this determinant is non-zero, then that means that given any initial data, that is given a tuple of numbers, an n tuple of numbers, I can always find constants k1 through kn such that k1 y1 plus all the way up to kn plus kn times yn will be equal to c1, and kn y1 prime all the way up to kn yn prime will be equal to the second initial data, right? Being able to solve that linear system where you put some vector of initial data over here is equivalent to having non-zero determinants. And once you can satisfy those initial conditions, and if all of these solve the homogeneous piece of the differential equation, then by uniqueness, this has to be the unique solution, and there has to exist a solution by the existence. So the thing that's really doing the heavy lifting is the existence and uniqueness theorem, and the Wronskian is just saying, can I, given any initial data, can I find a linear combination of these functions that satisfies that initial data? And the moment that you can do that, then you're done. Does that comment make sense?
Yeah.
Okay.
I have a question.
Yep.
So if we're asked to prove existence and uniqueness, would we just use the theorem, or would we like also show that the Wronskian is not a zero function?
So how to answer this? So essentially, what I have stated is the existence and uniqueness theorem for higher order linear differential operators, and I haven't proven that theorem. I've just given you conditions under which you know that you have existence and uniqueness on an interval. So the types of questions that I could ask you are, I could provide for you a higher order differential equation with some t0 and ask you what is the largest interval on which you are guaranteed a solution by the existence and uniqueness theorem. That's one question I could ask you. Another question I could ask you is, given a higher order differential equation and given a collection of solutions, is this collection of solutions a fundamental system for the differential equation? And technically for that, you'd have to check, first of all, that all of these satisfy the differential equation, and second of all, that the Wronskian of them is non-zero. But I don't see a circumstance in which you would prove that there is existence or uniqueness. Like the existence or uniqueness stuff, when you get conditions on it or series conditions, that's when you're dealing with nonlinear stuff. When you're doing nonlinear stuff, then you have to check, you know, derivatives, partial derivatives, and then determine if they're continuous on rectangles. But for here, I don't see such a question appearing very naturally. Does that make sense?
Yeah, that makes sense. Thank you.
Sure. Okay, any other questions? Okay, now I'm going to provide you with something helpful, or this is a good next topic for several reasons. What I'm going to discuss now is the real notion of linear independence and linear dependence. So what I've been saying, and this is kind of a sloppy way of teaching, is I've said that if the Wronskian of, say, two functions, y1 and y2, is not the zero function, then those two functions are linearly independent in a suitable way. And maybe it hasn't been very clear why I've said that word, linearly independent. So what I'm going to do now is I'm going to give the correct vector space definition of linear independence and linear dependence, and we'll see that this notion will coincide with the determinant not being zero. So it's been not such a big sin for me calling, if the Wronskian doesn't vanish, calling that linear independence of your functions. So definition. Functions f1 through fn defined on the, so these functions are linearly independent, or sorry, linearly dependent on an interval I if there exists a collection of constants k1 all the way up through kn, such that the ki are not all zero, and k1 f1 of t plus all the way up to plus kn fn of t is equal to 0 for all t inside the interval. So if you've had linear algebra, perhaps you recognize this as the way that you define when a collection of vectors are linearly dependent. So linearly dependent means that you can express 0 as some non-trivial linear combination of these functions. Notice that I can always get this expression to be 0 when all the ki are 0, right? If I have 0 times f1 plus 0 times f2 all the way up to plus 0 times fn, then that will always be 0. But here I'm saying, is there a second collection of constants, k1 through kn, where not all of them are 0, such that I can write 0 in this way?
Can you read what it says after where you wrote K1 F1 of t? The very bottom line.
For all t in I.
No, sorry, just like the whole bottom line, maybe.
Oh, right. So this is k1 times f1 of t plus, and then I did dot, dot, dots. So really what this means is plus k2 f2 of t plus k3 times f3 of t, all the way up to kn times f. And then as a convenient definition, f1 through fn are linearly independent. Oh no. Independent on I if they are not linearly dependent. Let's do an example. This is probably one of the, maybe I should do several examples of this, both in the function setting and just in the vector setting. So let's do the following. Show, so here's an example. Let's show that the functions 1, t, and t squared are linearly independent on the real line, on R. Okay. So what do I need to examine? Well, what I need to do is I need to take 3 arbitrary constants. So consider k1 times the function 1 plus a constant 2 times the function t plus a constant 3 times the function t squared, and ask, when is this the 0 function on R? Now, obviously, it's the 0 function whenever k1, k2, and k3 are all 0. But we should consider what would happen for other k's. So an idea is as follows. If this is the 0 function, then it must be 0 for all t. Let's pick 3 specific t's and see what k1, k2, and k3 have to be so that this function will be 0 at all those places. So pick t is equal to -1, t is equal to 0, and t is equal to 1. Sorry, 1. And let's just plug in. So at t is equal to 0, k1 of times 1 plus k2 of t plus k3 t squared evaluated at t is equal to 0 just becomes what?
K1.
Yeah, just becomes k1. If this is the 0 function, what does that mean k1 has to be?
0.
Right, that implies k1 is equal to 0. Okay, so already we know that k1 has to be 0 in order for this to be the 0 function. Now let's examine something else. So our function now looks like 0 times 1 plus k2 times t plus k3 times t squared. And let's evaluate this at t is equal to -1. What do we get?
K3 minus K2.
Yeah, k3 minus k2 must be equal to what?
0.
Must be equal to 0. And if I plug in 1, 0 times 1 plus k2t plus, sorry, this is getting a bit far, plus k3 t squared, and evaluate it at t is equal to 1, then I'll see that k2 plus k3 has to be equal to 0 as well. And then we solve this system. How do I get k3 to be equal to k2, but also have them sum to 0?
They're both 0.
Right. Thus, k2 is equal to k3 is equal to 0. And thus you see that the only way for this function, k1 plus k2t plus k3t squared, to be the 0 function is for all of the constants to be 0. K1 has to be 0, k2 has to be 0, and k3 has to be 0. So we conclude what about this triple of functions, 1, t, and t squared?
They're linearly independent.
Yes. Thus, 1, t, and t squared are linearly independent on R. I kind of just want to make contact with some other elements of linear algebra. Here I want to consider maybe some finite dimensional vector spaces. So I just want to give some examples, maybe in 2 real dimensions. So let's consider the vector 1, 1, and let's consider the vector -1, 1. Show that these are linearly independent. And here I have to change the definition a little bit because technically I only define linear independence for functions on intervals. Here what I mean is -1 and 1 and 1 and 1 are linearly independent if there does not exist constants k1 and k2 such that k1 times the first vector, -1, 1, plus k2 times the second vector, 1, 1, is equal to the 0 vector. Could you try to work this out for me? This isn't particularly complicated, right? Can someone tell me what I should do? I have k1 times -1, 1 plus k2 times 1, 1 is equal to 0, 0. is, I just should ask. Are people, I mean, everyone who's seen Calc 3, everyone here has been through Calc 3, right? So you're at least comfortable with some of these aspects of vector calculus. Is that correct?
Yeah.
Yeah, somewhat.
Yeah, somewhat. It might be a little while ago, but okay. Is there a way that I can rewrite k1 times -1 plus 1, or -1 comma 1?
You can distribute the k into the function.
I can distribute the k1 in, and I can distribute the k2 in. So this is the same thing as asking for -k1, k1 plus k2, k2 to be equal to 0, 0. What can I do with two vectors in the same vector space?
You can separate each
Just
vector.
add them.
I can add them together, exactly. So I get k2 minus k1, comma, k1 plus k2 has to be equal to 0, 0. If k2 minus k1 is equal to 0, what does that mean?
K1 equals K2.
K1 is equal to K2, and if K1 is equal to K2 and K1 plus K2 is equal to 0, then
Both are 0.
K1 is equal to K2 is equal to 0. So the point of me doing this is to try to tell you that these notions of linear dependence and linear independence have their roots in a very geometric idea, namely dimensions of vector spaces. So if I have two vectors which are linearly independent, then somehow I can reach anywhere in this two-dimensional vector space called R2 by walking along paths either a certain distance along the first vector and then another distance along the second vector. That's the kind of point. As a different example, let's consider the following thing. Let's consider the two vectors 1, comma 1 and the vector 2, comma 2. So show that 1, 1 and 2, 2 are not linearly independent. Could you do this for me?
You could just say k1 is -2 and k2
Exactly.
is.
Precisely. So k1 times 1, comma 1 plus k2 times 2, comma 2 equals 0 has a non-trivial solution given by k1 is equal to -2 and k2 is equal to 1. So here what I was able to do is I was able to write the 0 vector as a sum of these two vectors where the coefficients were non-zero. And this is getting to the essence of what it means to be linearly independent. So what I want to show you here is how in a finite dimensional vector space, linear independence is exactly what it sounds like. Do these two vectors lie on the same line? When they do lie on the same line, then they're linearly dependent. When they don't lie on the same line, they're linearly independent. So there's a very geometric way of understanding what linear dependence and independence means. You can already kind of see what to expect from these pictures. And then you see that this idea of, can I write the 0 vector as a non-trivial linear combination of my vectors, is capturing the right notion. And so that's why the definition for linear independence of a collection of functions on an interval is what it is. I'm trying to show you kind of where that idea or where that definition of linear independence came from. Is this okay?
So basically it's linear dependent if like it's parallel.
When you only have two vectors, that's correct. But let's consider the following. Now let's move up to three-dimensional space. And here's where the examples start becoming more interesting. Consider the following tuples. here I'll take 1, 0, 0, 0, 1, 0, and then 0, 0, 1. First, show that these are linearly independent. And then consider, let's take 0, 1, 0, 0, 1, 1, and then 0, 0, 1. And you should, so determine either linear dependence or linear independence for these triples of vectors, please.
Say -1, 1, -1.
For this?
Oh, for the bottom.
For the bottom one, yes. So what I'll say is that I'm sure what you said is correct, but you're a little too fast for me, so I'll call this star and star star. So for a linear combination of star to be 0, we see that k1, k2, and k3, this is equal to k1 times 1, 0, 0, plus k2 times 0, 1, 0, plus k3 times 0, 0, 1. This is equal to k1 plus 2 plus k1, k2, k3. If this is equal to 0, that implies k1 is equal to 0, k2 is equal to 0, and k3 is equal to 0. So this tuple is linearly independent, which I'm sure you already knew. However, over here, we've confined k1. So if I take -1 times 0, 1, 0, plus 1 times 0, 1, 1, plus -1 times 0, 0, 1, this is equal to 0, the 0 vector, right? And what that's expressing is that this vector, 0, 1, 1, lies inside the YZ plane spanned by these two vectors, right? Here I have the vector 0, 1, 0. Here I have the vector 0, 0, 1. And so what they span is the YZ plane. And my vector in the middle, 0, 1, 1, is a vector which lies inside the plane spanned by other two. So you see, as you grow in dimensions, this question of linear dependence or linear independence isn't so much, are you on a line, but do you live inside a subspace determined by the other vectors? Or can you hit this vector by paths using these two vectors? And of course, you can check linear dependence and independence using the determinant, right? The determinant of these three will be 1. The determinant of these three vectors will be 0. So are we slowly kind of becoming happy with our definition of linear independence?
Yeah.
Okay. So let's go back to the function case. And I want you to do 1 or 2 exercises for me, please. As some examples, how are we doing on time? As an example, please check if let's see what I want to do. Check if 1 plus t squared and 5 minus 4t squared are linearly independent on R. Please. Does everyone understand what I'm asking you to do?
Yes.
Mhm.
You all figured out if this is a linearly independent set or not?
I think it is, but I'm not like
Linearly independent or linearly dependent?
independent.
I think this is going to be a linearly dependent solution, and I can tell you why. One way of thinking about linear independence, so technically what you're trying to solve is k1 times 1 plus k2 times 1 plus t squared plus k3 times 5 minus 4t squared is equal to 0, and you're trying to find if you can, does there exist k1, k2, and k3, not all of them 0, such that this equation holds. What I'd like to offer you is kind of a different way of thinking about it that coincides more with the previous work, which is, can I write this vector as a linear combination of these two vectors? So here's what you kind of should write down when you're asked to check linear independence, but here's another idea. Let me call this V1, V2, and V3, okay? V2 minus V1 is equal to t squared, right? T squared plus 1 minus 1, which is equal to t squared. Do you agree?
Yeah.
Okay. Now, can I build this function 5 minus 4t squared out of copies of V1 and copies of V2 minus V1? The answer is yes. If I take 5 times V1 minus 4 times V1 minus V2, or V2 minus V1, this is exactly 5 times 1 minus 4 times t squared, which is equal to v3. Right? Is this okay?
Seems good so far, yeah.
But once I have some relation like this, some linear relation between v1s, v2s, and v3s, I can simplify this by just collecting terms. So 5v1 plus 4v1 if I distribute, so I get 9v1 minus 4v2 minus v3 is equal to 0. So what you should check is that k1 being equal to 9, k2 being equal to -4, and k3 being equal to -1 will actually get you 0. Does it work?
Yeah.
Yeah. Another way to think about this, maybe the more concrete way to go about this, is to just set up a big linear system involving this thing. So if I distribute everything, I'll get k1 plus k2 plus k2t squared plus 5k3 minus 4k3t squared is equal to 0. And then I collect terms associated to the power of t. So I'll get k1 plus k2 plus 5k3 is equal to 0. I've got nothing involving t equations, and then I have, what am I looking for? Yes, and now I need to collect t squared terms. Now I have k2 minus 4k3 is equal to 0. And the question is, will I be able to find non-trivial values of k1, k2, and k3 such that these two equations are satisfied? And here you have two equations and three unknowns. So you're going to be able to find a large collection of non-trivial k1, k2, and k3 that do the trick. Right? I could pick, for instance, here, I could pick any k1 or k2 and k3 that make this work, like say k2 is equal to 4 and k3 is equal to 1. And then I'll be able to find some k1 such that this whole thing is equal to 0. A lot of ways of thinking about the same problem. Does anyone have any questions about this process or either of these approaches to this problem?
Could you put your paper down a little bit? Thanks.
So for instance, if k2 is 4 and k3 is 1, then I have 4 plus 5 plus k1. Sorry, this is 4, is equal to 0. And we see that k1 being equal to -9 will work. Interestingly, this gives me the exact negative of this tuple that works. Here I have -9, 4, and 1, whereas here I had 9, -4, and -1. Any questions on this? Okay. If there are no questions on this, then I want to continue. And since I want to finish this section today and we only have 40 minutes left, I'm going to go a bit fast through the next thing. I won't give a full proof, perhaps. But now we have the following very helpful and useful theorem. F1 through Fn, sorry, I should use y's, I like y's better. Y1 through Yn form a fundamental system of solutions to L of yi is equal to 0 and some initial data, y of t0 is equal to y0, y prime at t0 is equal to a whole bunch of stuff. No, sorry. The initial data doesn't come up. These form a fundamental system of solutions to this higher order linear differential equation if and only if the y1 through yn are linearly independent. Okay. So what this is saying is that if you want to check whether you have a fundamental system of solutions, you can either calculate the Wronskian and see that it's non-zero, or you can do this more linear algebra approach and ask, is this collection of functions a linearly independent collection of functions on the interval containing some initial data that you're interested in? So in this sense, you see why I wasn't committing such a sin when I said things like this pair of functions is a linearly is a fundamental set of solutions if they're linearly independent, and then I check the Wronskian. I should have, if I say linearly independent, I should be checking linear combinations involving K1 and K2, but it turns out that checking linear combinations and seeing when it's 0 is the same as determining whether or not the Wronskian is 0. Does this make sense? At least, I mean, I haven't proven it to you, but is this a believable? Do you understand what I'm saying in this theorem, essentially?
Yeah.
Yeah.
Okay, great. Maybe the proof is discussed in the book, but maybe I'll just give a brief discussion of how to, so a sketch of proof. So in one direction, assume that the yi are a fundamental system of solutions. Then what we're going to do is we're going to take initial data essentially, well, what do I want to say here? I want to consider systems like K1 Y1 plus Kn Yn is equal to 0, K1 of Y1 prime plus Kn of Yn prime is equal to 0. So I'm considering a big collection of conditions where I want everything to be equal to 0. So I'm essentially specifying some initial data where I want the function to be 0 and I want all of its derivatives to be 0 at a particular point. Then K1 Y1 to the n minus first derivative all the way up to Kn Yn to the n minus first derivative being equal to 0. Okay. So essentially, if the yi form a fundamental system and there exists a K1 star all the way up through Kn star such that K1 star all the way up, K1 star Y1 all the way up to Kn star yn is equal to 0, then k1 star all the way up through kn star will be will give a solution to the IVP. But 0, 0 also gives a solution to the IVP. And by uniqueness of solutions, we see that the ki star all have to be equal to 0. So the idea here is you, if you have a collection of fundamental systems, or sorry, if you have a fundamental system of solutions, then you pick some points t0, and then you take initial data all zeros. There's one obvious solution to this IVP, and that obvious solution is take all of your constants ki to be 0, because then I just have 0 times y1 plus 0 times yn is equal to 0, and similarly 0 times this derivative all the way up to 0 times this derivative is equal to 0. So if I put all the ki's to be 0, then I get a solution. If there's another collection of ki's where they're not all 0, that would seem to imply that these functions are linearly dependent. But if there exists such a collection of ki's that are not all 0, then I get another solution to the IVP, which contradicts uniqueness of solutions to IVPs. Is this okay? Maybe I'll say, here is what you should remember from this. If the yi form a fundamental system and the yi are linearly dependent, then uniqueness breaks. Uniqueness of solutions to IVPs breaks. Remember that a fundamental system is a collection of functions such that every solution to the differential equation can be written in terms of them and can be written uniquely. So if we have a fundamental system of solutions, any solution to any IVP can be written in one way as a linear combination of these. But if we assume that they are linearly dependent, then we get two solutions to the same IVP. Questions here? I feel like people are not happy with what I just said. It's very quiet.
Could we maybe do an example?
Well, it's a little difficult to, let's see. So this isn't so, I can try to write some example for you, yes. The point of this theorem is that the Wronskian not vanishing is the same as the collection of functions being linearly independent. So as an example, I can show you a collection of linearly dependent functions, and then we can show that their Wronskian is 0. Would that be the type of example that you're looking for?
Sure, I think.
Right, like you can either pick a collection, there are like options that you can pick. you can either pick a collection of functions such that their Wronskian is 0, and then what you will see is that the collection of functions is linearly dependent, or you can pick a collection of functions whose Wronskian is non-zero, and then you can show that those are linearly independent. Alternatively, you can take a collection of functions which are linearly independent and show that their Wronskian is non-zero, or you can pick a collection of functions which is linearly dependent and show their Wronskian is 0. So which of those examples would you like to see?
Well, I guess I understand what you're saying now. So could you possibly, instead of doing that example, just clarify which of those cases is particularly surprising, I guess?
Oh, I wouldn't say any of them are particularly surprising, but how about we do it with this previous example of functions that we just found were linearly dependent. So as an example, we just showed that the following functions 1, comma, what was it? Let's make it easier. T squared and 5 minus 4 t squared are linearly dependent, right?
Yes.
This was more or less what we showed last time. Now let's show that the Wronskian of these 3 functions is 0. So here we're looking for the determinant of this thing is going to be 1, 0, 0. The derivatives of this guy are going to be t squared, 2t, and then 2. And then the derivative of this guy is going to be, well, it's going to be 5 minus 4 t squared. And then it's going to be, what, negative 8t. And then it's going to be negative 8. Did I take the derivatives correctly here?
Yes.
Okay. So what I'm going to do is I'm going to compute the determinant of this matrix. I can compute by taking this column, essentially. So what I can do is I can say this is going to be 1 times 2t times negative 8 minus negative 8t times 2 minus 0 times some minor. Here I'd be taking this minor, but I'm multiplying by 0, so it doesn't matter, plus 0 times this minor. But all that goes away. And so now I'm just asking, what is this thing? 2t times negative 8 plus 2t times 8. This is going to be equal to what function?
0.
This is the 0 function. Do you agree?
Yeah. Okay. I think this makes sense now.
Right. So if I start with linearly dependent functions, their Wronskian will be 0. If I start with linearly independent functions, their Wronskian will be non-zero, and vice versa. If I start with a bunch of functions whose Wronskian is 0, then they're linearly dependent. If I start with a bunch of functions whose Wronskian is non-zero, then those functions are linearly independent. Is this okay?
Yeah, I think so.
Okay. Great. Then let's put this behind us for the moment. And now we will essentially cover the next topic. Okay. Oh, one more remark. If C1, Y1, all the way up through Cn, Yn is the general solution to L of phi is equal to 0, namely, if this is the general solution to the homogeneous piece of the higher order linear differential equation, then the general solution to L of phi is equal to G of t is just C1, Y1, all the way up to Cn, Yn, plus capital Y, where L of capital Y is equal to G of T. So what I'm saying here is this first chapter, this is 4.1, this first section, tells you all of the things that you expected or that you knew from second order linear differential equations all hold up here. First of all, we have a good notion of what the initial data should be to get a unique solution. We have existence and uniqueness of solutions on intervals where the coefficients are continuous. We understand how to check whether you have a general solution. You either check the Wronskian or you check whether those functions are linearly independent. Those are equivalent checks. And once you're trying to ask about non-homogeneous higher order differential equations, well, first you find the general solution to the homogeneous differential equation, and then you find a particular solution. So pretty much everything that you expect carries over. Any questions on this?
Makes sense.
I'm glad to hear it. Okay, so then let's do 4.2. What were the only second order linear differential equations that we could actually concretely solve? What were the coefficients?
Coefficients are all constants.
Coefficients were all constants. We'll see the exact same phenomenon here. More or less, we can only solve, and by solve, I mean produce actual numbers. We can only solve when we have constant coefficients. So constant coefficients.
Can't we solve when we do the reduction of order thing?
Yeah, so there are two things there are two kind of comments here. First of all, there are some additional second order linear differential equations that we can solve, namely the Euler equations. Those we got by a change of coordinates. So those are some second order linear differential equations that don't have constant coefficients that we could solve. The reduction of order is a little different because in order to do reduction of order, you already need one solution. So if you have one solution to a second order linear differential equation, and even if the coefficients are not constant, then you can produce a second solution using reduction of order. But in all the reduction of order problems, you're always given the first solution. It might be very difficult to find the first solution to a second order linear differential equation. Is that okay?
Yeah.
Okay. So a general one of these will look like a0 y to the nth derivative plus a1 y to the n minus first derivative all the way up to a n minus 1 times y prime plus a n y is equal to 0, right? And once again, what should we guess is a solution to this?
Y equals e to the RT.
Yeah, we should look at exponential functions to be solutions. When is e to the RT a solution? And the answer is, if we plug in y is equal to e to the RT into this differential equation, we'll produce something very familiar. We'll get a times r to the n e to the RT, a0, plus a1 e to the, a1 r n minus 1 e to the RT, plus all the way down to a n minus 1 r e to the RT plus a n e to the RT is equal to 0. And if we factor out an e to the RT, we exactly have a0 r to the n plus a1 r to the n minus 1, all the way down to a n minus 1 r to the 1 plus a n, no r's, is equal to 0. And this is 0 exactly when r is a root of the polynomial a0 x to the n plus a n minus 1 x plus a n. So we're right back into very familiar territory. E to the RT is a solution to this higher order homogeneous linear differential equation with constant coefficients if and only if R is a root of this big characteristic polynomial, where now we're dealing with characteristic polynomials in higher degree, not just degree 2. So this is the characteristic polynomial. What we know is that e to the RT is a solution if and only if R is a root of the characteristic polynomial. Right? Do you see that this is exactly what we were doing for second order, with the only caveat that now we're dealing with polynomials of higher degree?
Yeah.
Great. Now you see why this whole theory is going to take us like 2 days to cover, even though we spent like 2 weeks on the second order stuff. Okay, over the complex numbers, does anyone know what the fundamental theorem of algebra says? The fundamental theorem of algebra is about polynomials factoring into linear pieces. Well, I'll just tell you. This is the fundamental theorem of algebra. Over the complex numbers, every polynomial with real coefficients can be written as a0 times x minus r1 times x minus r2 all the way up to x minus rn. Or in other words, over the complex numbers, we always have all of the roots that we have n roots for a degree n polynomial. So this corresponds to what you already know for degree 2 polynomials. There are some degree 2 polynomials with real coefficients which do not have 2 real roots. But once you allow complex roots, every single degree 2 polynomial can be written as a product of linear terms. This is exactly what the quadratic formula is telling you. You can break up any polynomial into some number times x minus a root times x minus a second root. So all that I'm saying here is that no matter how big your polynomial is up here, you always have n roots, where some of these roots might be complex and some of them might be repeated, but you can extract from this polynomial the data of n roots. So case 1. The Ri are distinct real numbers. What do you expect to happen here?
We can have all those like n different solutions.
Exactly. Then the general solution is C1e to the R1t plus C2e to the R2t plus C3 e to the r3t, all the way up to plus cn e to the rnt. So if you have a polynomial which factors as a bunch of, it just has a bunch of distinct real roots, then you can write out the general solution exactly like you'd expect it from the second order linear case, right? There we just had two of these. We just had c1 e to the r1t plus c2 e to the r2t. Here we're just saying, well, every time that you've got a distinct real root, that thing is a solution. So your general solution should just be a big combination of all of them. Any questions on this? Okay. So this is like the least, this is very expected behavior, right? No one is surprised by the things that I'm writing down, or no one thinks they're going to have trouble memorizing the formula for these general solutions, I think, right?
Yeah, right.
Okay, great. Case 2, there could be some complex roots. For instance, I could have my polynomial break up as some stuff times x minus lambda plus mu I. But then, does anyone know if one complex root appears, what else has to appear?
Its conjugate.
Yep, its complex conjugate has to appear. So then x minus, here it'll actually be plus lambda plus mu I. So if our real polynomial, and by real I mean it has real coefficients, a0 x to the n plus a1 x to the n minus 1 all the way down to an has a complex root lambda plus mu I, then the complex conjugate, which is lambda minus mu I, is also a root. Oh, sorry, I wrote this wrong. This should be minus, and then here we should have a minus. That was bad. Then the complex conjugate, lambda minus mu I, must also be a root. And you know exactly what type of solution we get from these, right? If lambda plus mu I is a root and lambda minus mu I is a root, what do I expect for solutions here?
E to the lambda t cosine.
E to the lambda t cosine of mu t and e to the lambda t sine of mu t will be among the fundamental solutions. So what I mean by this is, let's do the following example. Let's find the general solution to y to the fourth derivative plus y is equal to 0. Okay. What is the characteristic polynomial of this? Oh wait, do I want, let me do minus 1 here, actually, that'll be easy. Y to the fourth minus y is equal to 0. What's the characteristic polynomial?
That'd be x to the fourth minus 1 equals 0.
X to the fourth minus 1 is the characteristic polynomial, and I want to set it to 0. So I'm looking for the fourth roots of 1. Right? Does anyone know what the fourth roots of 1 are?
1 and negative 1.
1 and negative 1 are certainly in there. For instance, this factors as x squared minus 1 times x squared plus 1. What does x squared minus 1 factor as?
-1 and 1.
Yep, x minus 1, x plus 1. This factors as x minus I and x plus I. So essentially what you're saying, what we're seeing here is that here is 1, and then the fourth roots of 1 are all the points on the circle, such that if you, on the unit circle, such that if you multiply the argument by 4, you get back 1. So 1 just stays the same, but I squared, I cubed, 1. -1 goes -1, 1, -1, 1. So that's a fourth root of 1. And then -I goes -I. So here we're going 3/4 of the way around the circle. -I times -I is -1. I multiply that by -I, I get I. And I multiply by -I again, I get 1. Okay, these are the fourth roots of 1. So what is our general solution? What do we get from the -1 and +1 roots?
Just,
E to the negative t
yeah,
and
e
e to the t.
negative
C1 e to the t plus C2 e to the negative t. And then what do I get from the complex roots?
Would that be c3 cosine of t plus c4 sine of t?
Yep. I don't have any e to the lambda piece because lambda is 0. So I just get e to the 0, which is 1. So this is the general solution. Really, all I take here are all of the distinct real roots. And then for each pair of complex conjugate roots, I take one of them and I get the cosine and sine term out of this one of the pair of complex conjugates. Is anyone surprised by this answer?
I just want to clarify,
Sure.
you switched from x's to t's, right?
So what I've been doing is when I write down the complex, or when I write down the characteristic equation, I've been writing x's. But when you look at the roots of the characteristic equation, which in this case are 1, -1, I, and -I, then that becomes associated to the following solutions. So the passage from roots to solutions is e to the R1t,
Oh, I got you. Okay.
e to
Thank you.
the negative R2t, and then e to the it. Well, what do I do with this? I get a cosine of t, and then a plus I sine of t. So from this, I get t's out. Yeah. So I didn't
Gotcha.
really switch from x's to t's. I solved the roots in a polynomial in terms of x, and then I plugged those in the way I know how to get the roots. Or to get the solutions, I mean.
Gotcha. Thanks.
Okay, and the last thing that we need to sort out are repeated roots. Here is the one place where it looks a little bit different, or where it's not totally obvious what the answer is. But let me just write down the answer, and you'll find that it's also, once again, not unexpected. So for repeated roots, let's say that A appears as a root k times. Then a general solution will involve the following subset in terms of its fundamental solution. It'll be e to the at, t e to the at, t squared e to the at, all the way up to t to the k minus 1 times e to the at. So essentially, this ends up looking very similar to the repeated roots case when you just had a degree 2 polynomial. If you had a degree 2 polynomial and some roots repeated, then you knew that you had these two as your fundamental system. The point is, if a root gets repeated k times, then you get more solutions by just raising the power of the t in front of the e to the root times t. And this can be proven by induction, essentially. Proved by induction on k, if you so desire. Y'all have had discrete, right?
No.
No? Okay. Well, then I won't prove this. I wasn't going to prove it anyways, but all that I ask is that you know what the general form of a solution is if you have a bunch of repeated roots. And I think that this is also not too unreasonable to remember because it looks very similar to what you had in the 2 repeated roots case.
So these are only for homogeneous higher order.
Yes, these are only for homogeneous, but remember what I said at the beginning, well, what I said a half hour ago, is that the solutions to non-homogeneous are just the general solution to the homogeneous plus a particular solution. But yes, what I'm writing down are general solutions to the homogeneous differential equation.
So we don't know how to find those particular solutions, right? Like it's not just.
No, we don't. The same techniques that we learned for second order still work, at least in theory. Like there's no reason why you can't start looking for undetermined coefficients and start looking for variation of parameters. But those already became very difficult to compute in general, even in the second order case, and they just become worse and more difficult in the higher order case. So in general, the hard part now is finding particular solutions. Yeah. Because the general solutions to the homogeneous piece for constant coefficient higher order differential equations are pretty much known. There's something a little further that I want to say here with repeated roots, is that it's possible that you have a polynomial with repeated complex roots. So what if you have repeated complex roots? So for instance, I could have, what if the characteristic polynomial is something like x minus, and here I'll do 1 plus I times x minus 1 minus I times x minus 1 plus I, and then I have x minus 1 minus I, right? Each of these will multiply together to give a polynomial with real coefficients, and this will give me a polynomial with real coefficients. And so overall, I'll get some kind of messy polynomial in terms of real coefficients. But a priori, this is some characteristic polynomial that might appear. Does anyone have a way that they think that we should combine our previous ideas to get solutions? It's going to end up being pretty reasonable. Essentially, we get solutions by examining e to the 1 plus I times t, and also t times e to the 1 plus I t. So anytime that you're going to have a repeated root, then you should consider what happens when you multiply the most basic form by t. So these will both be solutions. And of course, I can always take both of the real parts associated to these complex solutions. So the general solution will be, what do I get from here? I get C1, here I get e to the t cosine of t, plus C2 e to the t sine of t. And then from these, I get plus C3 t e to the t cosine of t, plus C4 t e to the t sine of t. Do you kind of see how we go about finding the general solutions associated to these characteristic polynomials?
Yeah.
Yeah. So as I have only 1 minute left, but let's say I have something that looks like x minus r1 cubed, x minus r2, and then x minus lambda plus mu I, and then squared x minus lambda minus mu I squared. So now I'm kind of putting everything together. I've got 3 different roots, well actually 4 different roots, r1, r2, this complex number, and its complex conjugate. And I've got repetition everywhere. Then the general form for the solution here will be C1 e to the r1t plus C2 e to the, t e to the r1t plus C3 t squared e to the r1t. That takes care of this triple root. Plus C4, now I've got this root, e to the r2t. And now I've got to deal with these, but that'll look exactly like what I had up here. So I'll get plus C5 e to the lambda t cosine mu of t plus C6 e to the lambda t sine of mu of t plus C7 e to the C7t e to the lambda t cosine of mu of t plus C8 t e to the lambda t sine of mu of t. Right? It's kind of a simple formula. Every time that you've got repetition, you need to be increasing the powers of t in front of your solution. For distinct ones, you just get normal C4 e to the root t, and then whenever you have complex conjugates, you break them into the 2 real solutions. Is this okay? Any questions on this?
So it just looks really complicated, but it's just the exact same stuff that we've been doing for the second order.
Exactly. It's just the exact same stuff. The only thing that you should remember, the only new thing that I've really told you is that when you have a root that's repeated more than twice, you continue raising the power of t in front of the expected solution. So x minus r1 cubed, I need to get 3 linearly independent solutions out of this. The first one is just what you expect. The next one is I multiply the expected solution by t. And the third one is I multiply the expected solution by t squared. And then that pattern holds if you have repeated complex roots. Here, I have one expected root, namely e to the lambda plus mu it, I get two real solutions out of that, namely e to the lambda t cosine of mu of t, e to the lambda t sine of mu t. But since this is a repeated complex root, I also have to get two more solutions out of it, namely the ones that I get when I repeat. So I get t's in front of those solutions. I think that as you do a couple practice problems, these will start to feel pretty reasonable. Any further questions? I'm going to take your long silence as a no. So have a lovely afternoon. I'm going to take like a 5-minute break, so I'll be back at 1:10 for office hours. Have a lovely yes. Have a lovely afternoon, everyone.
Thank you.
Thank you.
Yeah.